Blocks A and B of mass 10 kilograms and 6 kilograms are placed on the inclined plane and released. We're asked to determine the force developed in the link. We're given the coefficients of kinetic friction between the blocks and the inclined plane. Mu A is equal to 0.1 and mu B is equal to 0.3. We're asked to neglect the mass of the link. I'll give you a couple of minutes to try to solve the problem, and then you can continue the video to see the answer. So step 1, again, is to write down what we know. MA is equal to 10 kilograms, MB is equal to 6 kilograms. We know that we have A and B which are connected with the link. We are given mu A and mu B, which means that we're dealing with friction. And we are asked to find the internal force between A and B. So what can we conclude from the problem statement? First, we're dealing with a system of particles. We have two bodies that are connected to one another, A and B. We know that friction is involved, so we will need to make use of the friction equation. And since we're dealing with a two-dimensional problem, 2D space means that we have to use the X and Y components. So step 2 is to draw the free body diagram. Since we're dealing with a system, we need to draw the free body diagram of both bodies. And if someone's interested, he can also draw the free body diagram of the overall system. So body A is actually subjected to its own weight, MAG, vertical down. NA is positive and vertical to the surface. Fi, which is the internal force, is along the link. Now you cannot know if it's directed towards the right or towards the left, but you can simply assume any. Here I have assumed Fi to be in the positive direction for A. Now concerning friction, it's always opposite to the motion, and since we're dealing with an inclined plane, the frictional force is also inclined, and its value is mu A and A. Now here again, notice I have selected a coordinate system which is aligned to the inclined plane, and that's because it will actually simplify the different equations. If you actually want to deal with a coordinate system that follows the horizontal and vertical axes, by all means you can do that. You'll definitely end up with the same answer. So for B, we can draw the free body diagram as well. The box is subject to the weight, MBG. It also has a normal reaction force, which is perpendicular to the inclined surface, and B. It has a frictional force which opposes motion, so it's towards the left, mu B and C. And finally, it has the internal force, which is applied by the link, Fi. Now notice Fi here is not towards the right in the positive sense, because you should always remember internal forces are always opposite in direction. So if you cut the link in half and you look at the two forces that are being developed on the left and on the right, they always need to cancel out. So if I have selected Fi for A to be towards the right, Fi for B must be towards the left. You won't get the correct final answer if you've written Fi towards the right as well for B, because it's not consistent with what we know. So internal forces are always opposite in direction. Next, we can draw the kinetic diagram. So for block A, we have MAAY and MAAX. Again, always assume a positive direction whenever you do not know the actual direction of the acceleration. We can do exactly the same for B, MBABY, MBABX. Now that we have drawn the two diagrams, we have a better understanding of the different forces and the acceleration. We can write down the different equations. Again, remember from the time plan, since we are looking for the forces, we need to write down the kinetic equations. We're working with a 2D space and we have two different bodies, so we must end up with a total of 4 equations, 2 for each of the bodies. So sigma fx equals max for A. Again, remember it's always good practice to draw the sign convention to avoid making mistakes. So we have Fi minus 0.1 NA plus MAG sine 30, which is the projection of the weight onto the new axis I have selected, is equal to MAXA. Similarly for Y, sigma Fy is equal to MAY. There is no way the two boxes will actually move upward, and detach from the surface. So MAY is equal to 0. Summing up the forces on the y-axis, we have NA minus MAG cosine 30 is equal to 0. Now writing the kinetic equations again for B, sigma Fx is equal to MAx, which is equal to minus Fi minus 0.3 NB plus MBG sine 30 equals to MABx. For the y component, we also know that AY is equal to 0, and then summing up the different forces along the y direction, we end up with the following expression. So we now have 4 different equations. The next step is to count the number of unknowns. So looking at all of the equations, we have Fi, which is a known, the acceleration of A, which is a known, the normal reaction NA, which is a known, NB, which is a known, and AB, which is a known. So we have a total of 5 different unknowns for 4 equations. This means that we need to add one more equation to the problem. Now, as I have said before, whenever you need additional equation, you can look to the kinematics. But here there's a hint and an additional equation that comes outside of the kinematic equations and actually comes from the fact that the link is rigid. And you should remember that for future problem. Whenever you have two bodies that are connected with a rigid link, they must move at the same rate. So one can write that AAX is equal to ABX. So that's the additional equation we need. We did not have to make use of the kinematic equations since we're dealing with a system which involves a rigid connection. So AA is equal to AB. We have 5 equations with 5 unknowns. We can easily solve the problem. So solving equation 2, which is only in terms of NA, we have NA equals to 84.96. Solving equation 4, which is also in terms of NB only, we get NB is equal to 50.97. Then from 5, noting that AA is equal to AB, which is equal to A, we can replace that in the 2 other equations of motion. So we'll end up with Fi plus 40.554 is equal to 10A for the first equation. And from the second equation, replacing NB and AB, we have minus Fi plus 14.14 is equal to 6A. So now we're left out with 2 equations and 2 unknowns. We can solve for Fi and A, and we'll end up with Fi equals to minus 6.3715 Newton, and A is equal to positive 3.42 meter per second square. Now a note about the signs we got for Fi and A. Since Fi is negative, we need to flip the direction in the free body diagrams. So for A, we have assumed Fi to be towards the right, it should be towards the left. And for B, we have assumed Fi to be towards the left, it should be towards the right. Now concerning A, since it's a positive value, we know that the direction assumed is correct. So A will move towards the right.